Hi friends, welcome to our YouTube channel Knowledge Academy. In this lecture, we are going to basically discuss about the vector calculus formulas in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel. And don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes from mobile. If any improvements in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So in this lecture, basically we are going to learn or do the revision of the vector calculus of mathematics in a very detailed manner. See, in the vector calculus, the first topic is the basics one. The first concept in the vector calculus is basics we are going to discuss, which is, see, any vector a bar is equal to, we can write in terms of the magnitude of that vector and also the unit vector. So therefore a bar is equal to the magnitude of that vector and also the unit vector. So now suppose there is some vector OP bar which is equal to xi cap plus yj cap plus zk cap, means suppose in a three coordinate system x, y, z and z. So this is basically a right hand coordinate system, because if you do the cross product of the x and y, we are going to get the direction of the z axis. So we are going to specifically call this as the right hand coordinate system. So in the right hand coordinate system, there is a point P which is x comma y comma z. So if you are going to draw a straight line from origin to that particular point, we are going to call that point as the vector which is going to join the origin and that point, we are going to call it as a position vector. So if you are going to mention that OP bar, which is final point minus initial point, which is x minus 0 I cap plus y minus 0 j cap plus z minus 0 k cap. So if you solve this one, we are going to get OP bar is equal to x I cap plus y j cap plus z k cap. So now here I want to know what is the value of the magnitude of that vector. So now basically I want to know what is the magnitude of that vector. So therefore, if you want to know what is the magnitude of the vector, means it is the distance from the origin to that particular point, which is under root over x square plus y square plus z square. So basically this vector is going to have some magnitude and also the unit vector. So if you want to figure out the value of the unit vector, which is equal to the vector by the magnitude of that vector, so therefore OP cap is equal to OP bar by the magnitude of that vector OP bar. So in this way we can figure out the unit vector, the magnitude of the vector, and also we can figure out the actual vector. Suppose let me assume there are 2 points on the three coordinate system, which are the P and Q, and suppose in the P point is x1 comma y1 comma z1, similarly the Q point is x2 comma y2 comma z2. So now I am going to draw a vector from P to Q. So here you can see the arrow is going to go from P to Q, so therefore we are going to call P as a tail, whereas the Q as the head. So therefore if you are going to mention the PQ bar, which is the final point minus initial point, or final position minus initial position, we are going to get the actual vector PQ bar. So therefore x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. So if you want to know what is that magnitude of that vector PQ bar, then it means that it is a distance from the point P to Q. So therefore under root over x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So if you know the value of the vector, we also know the magnitude of the vector. So by this way we can also figure out the unit vector along that direction, also we can easily figure out. So now we are going to learn about some of the important properties of the vector. So let me assume there are two vectors v1 bar and v2 bar in a three coordinate system. So therefore a point in a three coordinate system can be represented with the help of 3 points. So therefore v1 bar is equal to a1 comma a2 comma a3. Similarly v2 bar is equal to b1 comma b2 comma b3. Then what I am going to do is I am going to do the addition of these vectors. See, whenever I am going to do the addition of these vectors, means we are going to add the corresponding elements. So therefore we can say a1 plus b1 comma a2 plus b2 comma a3 plus b3. So this is we are going to call it as the net vector. Then I have already told you in a triangle method, means for any triangle to figure, suppose a triangle is going to get formed only when one of the third side is always greater than or equal to difference of the remaining two sides, and it should be lesser than or equal to sum of the remaining two sides. If this property is satisfied, then only we can say that a triangle is going to get formed. In the same fashion, the magnitude of the vector v1 bar plus v2 bar is always less than or equal to sum of the individual magnitude of the vectors, and similarly the v1 minus v2 bar also is less than or equal to v1 bar plus v2 bar. This is the property of either positive or negative. They are going to satisfy in this manner. Similarly, v1 bar plus v2 bar is greater than or equal to difference of the vector magnitude vectors, and similarly v1 bar minus v2 bar greater than or equal to v1 bar minus v2 bar. I have already told you these important relations in the complex functions itself. Means either with the help of two vectors we can either find a diagonal which is v1 bar plus v2 bar or v1 bar minus v2 bar. See, these both can become a diagonal of the, because of these two vectors we can figure out the diagonal. So always the third side vector length will be always greater than or equal to difference of the remaining two sides, and it should be always lesser than or equal to sum of the individual sides. So therefore we can say then only a triangle is going to get formed with the help of these three lines. Otherwise a triangle is not at all going to get formed. Suppose there is a vector v1 bar. So now what I am going to do is I am going to do the scaling of that vector. Suppose the scaling factor is k. Let me assume the k is some real number. Then if I am going to do the scaling means for each and every component of the vector v1 bar, I am going to do the multiplication of k. For each and every component I should multiply by k. So therefore we are going to get k into a1 comma k into a2 comma k into a3. Suppose if I am going to get a new vector which is a linear combination of the v1 bar comma v2 bar, so it means that k1 into v1 bar plus k2 into v2 bar means here we have to go for the k1 into a1 plus k2 into b1 comma k1 into a2 plus k2 into b2 comma k1 into a3 plus k2 into b3. Means if you get any vector which is a linear combination of the two vectors means it is also going to lie on the same plane of the two vectors. Now we are going to learn about some of the basic properties of the vector addition. See, a bar plus b bar is equal to b bar plus a bar means whether you can add in this manner or this manner, the resultant will be always same. So therefore we can say this is called as a commutative property, means the vector addition is going to satisfy the commutative property. Now a bar plus b bar and this resultant we are going to add with the c bar. It is also equal to adding of vector b bar plus c bar. The resultant of this combination we are going to add with the a bar. You can do in either of these process, still the resultant will be always equal. Then we are going to say that the vector addition is going to satisfy the associative property. And similarly a bar plus 0 bar is equal to 0 bar plus a bar is equal to a bar means if you are going to add any non-zero vector with a zero vector, then definitely you are going to get that non-zero vector itself. That we are going to call as the a bar plus 0 bar is equal to 0 bar plus a bar is equal to a bar. Similarly, if you do subtraction of two similar vectors, we are going to get a null vector. So this is basically a null vector. It has to be like this one. So now we are going to discuss about the dot product of the vectors. Basically with the help of vectors, whether we can go for the cross product or the dot product. So now we are going to discuss about the dot product of the two vectors. See, let me assume there are two vectors a bar and b bar. See, a bar means actually I am assuming that this is a three coordinate system. So therefore we are going to mention the any vector with the help of three quantities. So a1 comma a2 comma a3. Similarly b bar is equal to b1 comma b2 comma b3. So now this is a vector a bar and this is a vector b bar. Then this theta is called as the angle between these two vectors a bar comma b bar. This theta can be either 0 to 180 degree. It can lie from 0 to 180 degree. Now what is the dot product formula? A bar dot b bar is equal to magnitude of the vector a bar into the magnitude of the vector b bar into cos theta. Theta is the angle between the a bar and the b bar. It indicates that always if you are going to do the dot product of two vectors, we are going to get the resultant is also a scalar, or we are going to get some numerical value. That is the reason the dot product is also called as the scalar product, because the output is always a scalar quantity. So whether you can go for in this process, in other process also, just do the multiplication of the corresponding elements and then overall do the addition. We are going to get the dot product of the two vectors. So therefore a1 b1 plus a2 b2 plus a3 b3. And if you are going to do the dot product of the two similar vectors, then what you are going to get is, if the dot product of two similar vectors means we are going to say the angle between them, or we can say simply if they are parallel, then theta is equal to 0, so cos 0 is 1. So therefore here we are going to get 1 as the result. So the dot product of two corresponding unit vectors will be always equal to 1. So therefore I bar dot I bar is equal to j bar dot j bar is equal to k bar dot k bar is equal to 1. But if you are going to do the two vectors which are orthogonal to each other. See, whenever we are going to the dot product of two orthogonal vectors means the angle between these two vectors is 90 degree. So cos 90 will become 0. So therefore, if we are going to the dot product of two orthogonal vectors, then definitely the dot product will be always equal to 0. Similarly, if we are going to the dot product of two vectors which are the unit vectors but they are orthogonal, then definitely their resultant value will become 0. So I bar dot j bar is equal to j bar dot k bar is equal to I bar dot k bar is always going to give you a result 0. So therefore, this is the sum of the important properties of the dot product. So dot product is also called as a scalar product because the output is always a scalar quantity. So now we will discuss some of the important properties of the dot product, which is a bar dot b bar is equal to b bar dot a bar. Means whether you can go for a bar dot b bar or b bar dot a bar, always the resultant will be always same. That is the reason we are going to say that the dot product is always going to satisfy the commutative property. And similarly, a bar dot of k1 b bar plus k2 c bar is equal to, here we can take this dot product inside, so therefore k1 into a bar dot b bar plus k2 into a bar dot c bar. So therefore we can say here you can go just like a normal multiplication, then you are going to get the same as this one. So either you go for this process or either you go for this process, still you are going to get the same result. See, basically the geometrical meaning of the dot product means just finding about the component of one vector in the direction of the other vector. So the geometrical meaning of the dot product means finding out the component of one vector in the direction of the other vector. That is called as the dot product. And if you are going to do the dot product of similar vectors, which is the a bar dot a bar is nothing but it is magnitude of the vector whole square. So therefore a bar dot a bar is equal to magnitude of that vector whole square. We are going to get the same result. So therefore, if the magnitude of any vector is equal to 0, only if a bar is a null vector, means only a null vector for each and every component is 0, then only their length will become 0. Otherwise, for any non-zero vector, always the magnitude will be always not equal to 0. If it is equal to 0, it indicates that is compulsory a null vector. And the magnitude of the dot product will be always lesser than or equal to magnitude of a bar into magnitude of b bar, because here there is a cos theta. So cos theta can lie between -1 to 1. So therefore we can say definitely this overall magnitude of the dot product will be always lesser than or equal to magnitude of the vector a bar into magnitude of the vector b bar. See, whenever the dot product of two vectors is equal to 0 means, I have already told you that a bar and b bar are said to be orthogonal vectors. Means whenever the angle between them is 90 degree, so therefore cos 90 will become 0. So therefore we can say whenever this a bar and b bar are orthogonal, the dot product will be always equal to 0. If theta is going to lie between 0 to 90 degree, then what is going to happen is, in this range, the cos is always positive. So therefore we can say that the a bar dot b bar will be always greater than 0. But if theta is equal to 90 degree, then cos 90 will be always equal to 0. So therefore the dot product will be always going to give you a result of 0. But if the angle is going to lie between 90 to 180, then in that range we can say that the cos function is negative. So therefore definitely the dot product is nothing but it is lesser than 0. Suppose if theta is equal to 0, then we can say that here whenever theta is equal to 0 means cos 0 is equal to 1. So therefore now a bar or b bar is equal to just magnitude of vector a bar into magnitude of vector b bar. Then we can say that a bar or b bar are said to be collinear vectors, or also we can say that these are the parallel vectors. Means if any two vectors, if their angle between them is 0 means they are nothing but collinear vectors, or you can also call it as the parallel vectors or collinear vectors. So this property also I have already told you in the complex functions, which is the magnitude of the vector a bar plus b bar whole square plus the magnitude of vector a bar minus b bar whole square is equal to 2 times of the magnitude of vector a square plus magnitude of vector b square. Means I have already told you with the help of, means if you know the parallelogram, this is called as the parallelogram. This is the diagonal of one parallelogram. The diagonal of the parallelogram is equal to, just we are going to do the addition of the four sides, square of addition of lengths of four sides we are going to do. So we are going to get this relation. This property I have already told you in the complex functions. Then the projection is nothing but, if you want to know what is the projection of vector a bar on the b bar, I want to figure out, which is a bar dot b bar by b bar dot b bar into b bar. See, a bar dot b bar is nothing but a scalar quantity, and similarly b bar dot b bar is again a scalar quantity. So finally we are going to get this scalar value. Scalar into vector is again a vector. So therefore this we are going to get a vector. Means the projection of A bar and B bar is nothing but basically we are going to find the what is the vector in the direction of B bar with the help of the component of A bar on the B bar. Means first thing is you have to find what is the component of A bar on the B bar, and then you have to find what is the vector B bar unit vector. Then you have to do the multiplication of the component of vector A bar and B bar and also the unit vector of B bar. Then we are going to get this result. So therefore we can say the projection of A bar on B bar is equal to A bar dot B bar by B bar dot B bar into B bar. So now we are going to learn about the vector cross product. Means that we can do the two vectors in the dot product or the cross product. So now we are going to specifically learn about the cross product. See, suppose there are two vectors A bar and B bar. So if you are going to do the cross product of two vectors A bar cross B bar, then you are going to get basically a vector. That vector is going to have some length and also some unit vector. That length will be magnitude of A bar into magnitude of B bar into sine theta, where theta is the angle between the A bar and B bar, and this n cap is called as the unit vector of this cross product. Means this is basically a unit vector. And if you want to specifically only know the magnitude of this A bar cross B bar, then you have to take only the magnitude part but not the unit vector. So therefore magnitude of A bar into magnitude of B bar into sine theta. So suppose this is a vector A bar and this is a vector B bar. So you can see clearly theta is the angle between the vector A bar and also the vector B bar. So therefore now we can say here n cap, this n cap is called as the unit vector. It is perpendicular to the both the vectors A bar and B bar. So if you want to know what is the direction of this normal vector, just you have to go for the, you have to curl your fingers from the first vector to the second vector. The first vector is A bar and the second vector is B bar. So you have to curl your right hand fingers from the first vector A bar to second vector B bar. Then the thumb direction is going to give you the direction of this cross product of this vector, which is n cap. So therefore always this n cap will be always perpendicular to both the vectors A bar and B bar. And here this is nothing but basically, suppose if you are going to draw a parallelogram, if you are going to draw the parallelogram with the help of these two vectors, then the net area of the parallelogram is nothing but the cross product, the amount of the cross product of this one. So therefore this is basically going to give you the area of the parallelogram formed by the two vectors A bar and B bar. So the amount of A bar cross B bar is nothing but it is the area of the parallelogram made by the vector A bar and B bar. But if you want only the half of this one, then we are going to get the area of the triangle formed by these with the help of these two vectors. So area of the triangle made by A bar and B bar. So therefore basically the magnitude of A bar cross B bar is going to give you the area of the parallelogram which is made by vector A bar and B bar, and half of magnitude of A bar cross B bar is nothing but it is basically area of the triangle made by the A bar and B bar. So now we will discuss some of the important properties of the cross product. So A bar cross B bar is equal to minus of B bar cross A bar. See, we can see clearly that this cross product is not going to satisfy the commutative property. And also if A bar cross B bar is equal to 0 means when A bar or B bar are said to be collinear vectors or the parallel vectors. Whenever there are two vectors are parallel vectors, then definitely theta is equal to 0. So when theta is equal to 0, we can say sine 0 is nothing but 0. So therefore the cross product will be always equal to 0 for parallel vectors or the collinear vectors. So now A bar plus B bar cross C bar is equal to A bar cross C bar plus B bar cross C bar. And K1 into A bar plus K2 into B bar, cross product of C bar is equal to K1 into A bar cross C bar plus K2 into B bar cross C bar. So now here this is a vector I, J and K. So this we are going to assume the anti-clockwise is positive. So definitely the clockwise will be negative. See, I bar cross J bar will become K, J bar cross K bar will become I, and K cross I will become J. But if you go for the reverse process, which is J cross I will become minus K, and similarly K cross J will become minus I, and similarly I cross K will become minus J. But if you do the cross product of two similar vectors, I have already told you for two similar vectors, the angle between them is, or we can say two parallel vectors or collinear vectors, definitely the angle between them is 0. So cosine 0 is nothing but 0. So therefore I cross I is nothing but 0 and J cross J is nothing but 0, and similarly K cross K will be 0. Suppose the vector A bar in a three-dimensional coordinate system, which is A1, A2, A3, and B bar is equal to B1, B2, B3. Then the cross product of the two vectors A bar cross B bar is equal to just do the determinant of this matrix, which is I, J, K, A1, A2, A3, B1, B2, B3 means just take the vector A bar components in this row and the components of vector B bar in this row. Then do the magnitude of this one we are going to get. So find the determinant of this matrix, then we are going to get the resultant vector, which is called as the A bar cross B bar, which is I into A2 B3 minus A3 B2 minus J into A1 B3 minus A3 B1 plus K into A1 B2 minus A2 B1. So like this we are going to get the overall cross product of the two vectors A bar cross B bar. So now I want to find what is the unit vector of this cross product vector. I want to find what is the unit vector of this cross product, which is n cap is equal to A bar cross B bar by the magnitude of the A bar cross B bar. And if you are going to find in this manner, which is A bar cross B bar dot C bar means is equal to, here see we can write, see replace A by B, B by C and C by A. So we are going to get this one. So therefore now just what you are going to do is just take the components of A bar initially A1, A2, A3 and B is B1, B2, B3 and C bar is C1, C2, C3. Just find the determinant of this one. Just find the determinant of this one. We are going to get the volume of the parallel pipe, or it is made by A bar comma B bar comma C bar, means always take only the absolute value, means take only the positive value, because volume is always going to give you a positive value. So therefore if it is a negative also, still you have to go for take down the positive value. So therefore we can say is A bar cross B bar dot C bar is equal to, or just replace A by B, B by C and C by A. So you are going to get this one. Again if you replace in the reverse process also, still you are going to get the same result. So therefore this we are going to call it as the amount of volume of parallel pipe, means suppose if you, with the help of these three vectors you can make some parallel pipe, so you can make some cuboid. So the amount of volume enclosed by that we can figure out with this expression. Suppose C bar is equal to K1 A cap plus K2 B cap B bar. So therefore you can see clearly this C bar is nothing but it is a linear combination of the two vectors A bar and B bar. Means this C bar is going to lie in the same plane of A bar and B bar. It indicates that, see, if the three vectors are in the same plane, then definitely you can't make any three-dimensional object, means we can say the volume enclosed by it is 0. So therefore we can say that if you are going to use this principle again, which is A1, A2, A3, B1, B2, B3 and C1, C2, C3, then definitely this determinant is going to give you 0, because we can't make any three-dimensional figure if all the three vectors are going to lie in the same plane. So because of that reason only we are going to say that A bar comma B bar comma C bar are said to be coplanar vectors or linearly dependent vectors, means the vector C bar is going to depend upon the vector A bar and B bar. Because of that reason only this vector C bar is going to lie on the same plane of the vectors A bar and B bar. So therefore we can't make any three-dimensional object. So definitely if there is no three-dimensional object, then definitely the volume enclosed by it is nothing but 0, or simply we can say that the vector C bar is going to depend on the vector A bar and B bar. If suppose A bar, B bar, C bar are linearly independent vectors, means linearly independent vectors means with the help of one vector we can't, means by using any two vectors we can't make the vector C bar, means they are not going to lie on the same plane. If they are not going to lie on the same plane, it indicates that we can make a three-dimensional object. So whenever we are going to make a three-dimensional object, then definitely the volume is not equal to 0, or simply if you make a matrix of A1, A2, A3, B1, B2, B3 and C1, C2, C3, and if you are trying to find the determinant of this matrix, then definitely their determinant will be not equal to 0, because we are going to make a three-dimensional object. Because of that reason only its determinant is never equal to 0. See, this is the very basic formula in the vector calculus, which is A bar cross of B bar cross C bar is equal to, take this bracket in the two sides and here just go for the dot product, which is, now see here, just go for the A bar dot B bar of C bar. Now just do the interchange B bar and C bar, you are going to get this result. So if you want to know what is the cross product of this nature, then same as the previous one. So this will be same as the previous one. This both are same. Only thing is here, now we are going to interchange these two parameters. Now we are going to interchange, then we are going to get, means we are going to interchange these two parameters. So we are going to get this result. So therefore if you try to remember this one, then it is easy to go for this one also. So therefore A bar cross of B bar cross C bar is equal to, take two brackets here, keep a negative here. First is A bar dot B bar C bar. Now just try to interchange these two things, then we are going to get here. So if you are going to find this one, these both are same. This initial value is same. Only thing, if you want to figure out this one, just do the interchange of this one. So we are going to get this one. So therefore now these both are never equal. So therefore A bar cross B bar cross C bar is never equal to A bar cross of B bar cross C bar. These are both never equal. So there is a scalar number k. So you can see here k. See, you can take k into A bar cross B bar, or you can take k outside, which is k of A bar cross B bar, or you can take inside with respect to B, so therefore A bar cross of K B bar. So no matter whatever the way you are going to do, still you are going to get the same result. And similarly, A bar cross B bar dot C bar means here replace A by B, B by C and C by A, you are going to get this one. Again replace B by C, C by A and A by B, we are going to get this one. See, always the volume enclosed by these objects with the help of these three vectors A bar, B bar, C bar is same. So therefore, no matter whatever the process you are going to do, still you are going to get the same result. So now I am going to find what is the gradient of a scalar field. Basically, the gradient of a scalar field will be, or we can say the gradient of any scalar function will be always perpendicular to the surface, and it will be always in the increasing direction of that surface. So the gradient of f is basically a scalar field or scalar some function. So therefore we can write it simply, which is del f. So therefore, as del is a vector quantity which is going to have dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap into f. So you have to multiply f for each and every quantity. So you are going to get dou f by dou x into I cap plus dou f by dou y into j cap plus dou f by dou z into k cap. So therefore this is basically a vector quantity. So therefore the grade f is always nothing but it is a vector quantity. So now we are going to learn about the geometric interpretation of the gradient f. So the meaning of the geometric meaning means, suppose this is a scalar function, means the f is a constant, some scalar function. So if you are going to find out the gradient of the scalar function, means it is a vector, it will be always perpendicular to that surface, and also its direction is in the increasing direction of that scalar function. And also, so therefore, as it basically a vector, this vector will have definitely the magnitude and also unit vector. So this is a unit vector, it will be always perpendicular to that scalar function. Suppose if you are going to find what is the directional derivative, means suppose this is a scalar function, f is equal to constant, so you have figured out the value of the gradient of the scalar function. It is in the perpendicular to this scalar function. So now what I am going to do is, I am going to take some vector which is b bar. So now in this vector I want to find what is the component of this gradient function. In this vector I want to find what is the component of this one. So you can see clearly theta is the angle between these two vectors, del f and the b bar. So now I want to find what is the component of del f on this vector b bar, means these 2 points. You can see clearly this is called as the component of this del f on this vector. So I have drawn it again. So now this is del f magnitude and this is the angle theta. So therefore cos theta. So therefore mod del f cos theta is nothing but this is the component of del f on the vector b bar. So now you can write it another fashion, which is b bar dot of del f by b bar magnitude. So if you expand this one, we are going to get mod of b bar into mod of del f into cos theta. So mod b are going to get cancelled. So finally we are going to get the same result. So therefore, so now this is called as the net resultant formula, which is b bar dot of vector del f by magnitude of the vector b bar. So the directional derivative of f at point P in the direction of the b bar is, just do the dot product of these two vectors, which is b bar dot del f at that point by magnitude of that vector b bar. So or simply this b bar by magnitude of vector b bar is nothing but is a b cap. So b cap dot product of del f point. So then we are going to get the same result. So therefore now here this is called as the directional derivative of the gradient of the scalar function in the direction of the vector b bar. Means it is just nothing but it is just a finding the component of the vector del f in the direction of the vector b bar. So the maximum possible rate of change of the directional derivative is nothing but, see, if you want to know what is the maximum possible rate of change, means see that component is nothing but mod del f cos theta. It will be maximum only when cos theta is equal to 1, but cos theta is equal to 1 only when theta is equal to 90 degrees. So therefore we can say clearly that the angle between the del f and the vector b bar must be equal to 90 degrees. Then only we are going to say we are going to get the maximum amount of change. So therefore the maximum possible rate of change of the directional derivative when the theta is equal to 90 degrees. So therefore now we are going to get mod del f at that point, means cos theta is nothing but 1. So this, if you find the magnitude of this one, this we are going to get the maximum possible rate of change of the directional derivative we are going to get at that particular point. So now we are going to learn about the other important concept, which is the divergence of any vector field. Suppose f bar is nothing but the capital F bar is a vector field. Now we are going to take the three-dimensional, so therefore it will be f1 comma f2 comma f3. So divergence of f bar, we can write it another form, which is del dot f bar. So this is nothing but a dot product of two vectors, then definitely the resultant will be a scalar quantity. So therefore del is nothing but dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap, dot product of f1 I cap plus f2 j cap plus f3 k cap. So if you are going to do the dot product, means doing the corresponding elements, just we are going to do the multiplication. We are going to get dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. So this is basically a scalar quantity. Means basically the divergence is going to tell you, is there any diverging nature of the vector field. We are going to figure out with the help of this divergence parameter. Suppose if its value is not equal to 0, means there is some amount of outflow or inflow. But if it is equal to 0, means there is nothing like outflow or inflow, means, or simply we can say the outflow is equal to inflow, means there is nothing like diverging nature of that field. So now we are going to learn about the other concept, which is the curl. Suppose is the vector f bar, it is in a three-dimensional coordinate system, which is f1 comma f2 comma f3. So now we are going to find what is the curl of the vector f bar. So simply we can write which is del cross f bar. See, it's I cap, j cap, k cap. This is dou by dou x, dou by dou y, and dou by dou z, and this is f1, f2, f3. So if you find the determinant of this matrix, which is I into dou f3 by dou y minus dou f2 by dou z minus j into dou by dou x into f3 minus dou by dou z into f1 plus k into dou by dou x into f2 minus dou by dou y into f1. So you can try to figure out this expression. Finally, you are going to get the resultant as this cross curl of this vector. See, basically this is nothing but it is going to give you, this operator is going to give you, is there any curling, is there any rotational mechanism is going to present in that vector field or not. We are going to check with the help of this operator. If it is not equal to 0, means yes, there is some amount of curling is going to get present. But if it is equal to 0, means we can say blindly that there is nothing like rotational mechanism is going to present. So this is basically a very important formula, which is W bar is equal to half of the curl of F bar, where W bar we are going to call it as the angular velocity, whereas F bar is nothing but linear velocity. It's a very important relation between the angular velocity and also the linear velocity, which is W bar is equal to half of the del cross F bar. So W bar we are going to call it as the angular velocity, whereas the F bar we are going to call it as the linear velocity. It's a very important concept because there are a lot of questions are being asked on this concept. So I recommend to remember this formula, which is W bar is equal to half of del cross F bar. So therefore W bar we are going to call it as the angular velocity and F bar we are going to call it as the linear velocity. So now we are going to learn about the vector line integral. It's a very important way of doing the line integral. Suppose we are going to find what is the line integral of vector f bar and d bar. On some path, on that path we are going to do the dot product of this two vector, which is f bar and d bar. So dr bar is nothing but dx I cap plus dy j cap plus dz k cap, whereas f bar is nothing but f1 I cap plus f2 j cap plus f3 k cap. So if you are going to the dot product of these two vectors, means doing the multiplication of the corresponding elements and then do the net addition. So therefore f1 into dx plus f2 into dy plus f3 into dz, and then do the integration across that path. That vector line integral is independent of path of integration if f bar is gradient of some scalar function f, x comma y comma z. Then the integral depends only on the endpoints. It's a very important concept, which is this line integration is independent of the path. This line integration is independent of the path only when this vector f bar, when this vector f bar is a gradient of some scalar function, then we can definitely say that this line integral is independent of the path you are going to travel, but it only depends upon the initial position and also the final position. This is the only case when this vector field is a gradient of some scalar function. Otherwise, we can say blindly that it is going to depend upon the path it is going to get travel. So this vector line integral is independent of the path of integration. If f bar is a gradient of some scalar function field, then the line integral is going to depend only on the endpoints, or simply we can say that the field is said to be conservative in nature. So f bar is nothing but which is the del f, means this vector f bar is equal to some gradient of some scalar function f, or simply we can write which is df by dr. So if you substitute here, this dr and dr is going to get cancelled. If you substitute this f bar in this manner, so dr are going to get cancelled. So integration of df is nothing but f. So therefore we have to substitute this f and this substitute the initial point on the final point, then find the f final point minus f initial point. If substitute, then you are going to get the overall result of this line integral across that path. So therefore we are going to get the net result. So this is a very important thing. See, which is if the vector f bar is the gradient of some scalar function, then definitely we can say that here the line integral is independent of the path which is going to travel, but it only depends on the initial and the final position. Or we can simply say that that field is said to be conservative in field. Means f bar is nothing but f1, f2, f3, whereas del f is nothing but dou f by dou x, dou f by dou y, and dou f by dou z. Means we are going to compare the corresponding elements because both are equal. So therefore f1 is equal to dou f by dou x, f2 is equal to dou f by dou y, and f3 is equal to dou f by dou z. So now what we are going to do is, with the help of these things, now with the help of this find f and cross check. So with the help of this one, do the partial integration with respect to x here, and with respect to y here, and with respect to z, and try to find the unit terms and keep some constant k, and try to figure out the cross check also whether it is going to satisfy or not. If we are going to get this satisfaction only, then only we can say it is independent of path, otherwise it is going to depend upon the path. So dou f by dou x is equal to f1, dou f by dou y is equal to f2, dou f by dou z is equal to f3. Then only independent of path. If not matching, then it depends upon the part of integration. Means try to do partial integration with respect to x, with respect to y, and with respect to z, and find f. It's the function of take some unit terms and constant, and try to do the cross check also. If it is going to get satisfied, then only we can say that that line integral is going to be independent of the path travel. Otherwise, it is going to depend upon the path we are going to get travel. So therefore, simply we can say del cross f bar is equal to 0, means f bar is said to be equidirectional and the conservative. Means here the curl of f bar, when f bar, see this is the only case when f bar is the gradient of the scalar function, then only we can say that the curl of f bar is equal to 0, or we can say the closed work done in that field, conservative field, will be always equal to 0. This is the meaning of that one. So therefore curl of f bar means there is no curling, or we can say this field has no curling, or it is also a conservative field, and we can simply say that the work done in the closed loop will be always equal to 0. So these are the things that we can estimate from this relation, which is del cross f bar is equal to 0 whenever that f bar is the gradient of some scalar function, or simply we can say this field is nothing but irrotational field and also conservative field in nature. Means the work done in that field is independent of the path travel, but it only depends upon the initial and the final position, and also we can say that the closed work done will be always equal to 0. Some more simple concept one we are going to learn, which is if f bar is equal to gradient of some scalar function, or simply we can write del f. Then if you are going to do the closed line integral, means if you want to find in a closed line in this path, what is the line integral I want to figure out in this closed path, means initial point is equal to final point. So f bar dot d bar is nothing but, just now I told you, which is f bar we can replace del f is nothing but dou f by dou x. So dou r cancels. So integration of del f is nothing but, means df is nothing but f. So f, for this f we are going to substitute both as same point because initial point is equal to final point. So therefore now if the difference of f of final point minus f of initial point, we are going to get 0 because initial point is equal to final point. So therefore we can say the closed line integral of f bar dot d bar is equal to 0 whenever f bar is the gradient of some scalar function, or simply we can say if you are going to convert this closed line integral into open surface integral with the help of Stokes theorem, we are going to get this relation, which is curl of f bar is equal to 0, means curl of gradient of some scalar function, because this f bar is del f. So therefore curl of gradient of some scalar function will be always equal to 0 no matter whatever that scalar function it can be, it is always going to be 0. So therefore we can simply say that this f bar is said to be irrotational, means there is no rotational mechanism, and also it is also said to be a conservative field. Suppose now we are going to learn some more general concept. Suppose here this is a two coordinate system, and I want to find the line integral from the initial point to the final point, where initial point is p of r1 and the final point is p of r2. So initial point to final point, I want to find what is the dot product of these two vectors over this line integral. So basically I am going to do the line integral over this part. Then I want to find what is the overall answer I want to figure out. So now we can write r is nothing but x comma y comma z. So r of t means it is a nature of time, x of t, y of t, z of t. So t is going to lie between t1 to t2. So r of t1 will going to give you the initial point, and r of t2 is going to give you the final point. So this f of r, now we are going to convert in terms of the f of t, means we are going to compare, we are going to convert from one domain to the another domain. So now f bar dot dr bar, from the initial point to the final point. Now we are going to convert this into one parameter, which is T1 to T2. Means if you are substituting T1, we are going to get initial point, and if you are going to substitute T2, we are going to get the final point. Then this f bar we are going to transfer it to f bar of t, means f of t dot product of r bar of t, because r bar of t, if you replace this one dr of t by dt, so dt cancels, we are going to get the same result. So therefore f of t means it's a vector, so f of t dot product of r dash of t into dt, so we are going to get the same result. So this is a simple way of converting from one domain to another domain. Means in this domain everything is the same parameter. So now we can easily do the simplification and try to get the result. Now we are going to learn about the theorems which are very useful, which are the Stokes theorem. See, basically Stokes theorem is nothing but here, with the help of a closed line, you can enclose a open surface. So therefore now it is going to basically relate a closed line and an open surface. So closed line integral of f bar dot dl bar is equal to open surface integral of curl of that vector f bar dot product of dA bar, or surface vector dA bar. So basically if you take any dA, it is basically area vector, so a small amount of dA and the normal vector n cap. So therefore dA bar, so dA bar is nothing but dA into n cap. So if you take f bar, so f bar is nothing but f1 x cap plus f2 a cap plus and f3 az cap, and dl bar is nothing but dx x cap plus dy a cap plus dz az cap. So if you do the dot product, we are going to get f1 dx plus f2 dy plus f3 dz. And similarly curl of vector f bar, if you do the curl of vector f bar and do the dot product with respect to dA bar, then we are going to get, so dA bar is nothing but dy dz ax cap dx dz ay cap plus dx dy az cap. So if you do the dot product, finally we are going to get, this is the relation we are going to get. So therefore this is nothing but, it is relating a closed line integral with respect to a open surface integral. Green's theorem is a special condition of the Stokes theorem. Green's theorem is a special condition of the Stokes theorem. Means here now we are going to assume that z is a constant. When z is a constant, definitely dz will be 0, and here also dz will be 0. So only this parameter or this term is going to get remain. So therefore the surface integral of dou f2 by dou x minus dou f1 by dou y into dx dy is equal to the closed line integral of this parameter, this, as dz is equal to 0, so this parameter term will become 0. So therefore only these two terms are going to get remain. So therefore closed line integral of f1 dx plus f2 dy. So therefore simply we can say the closed line integral of f1 dx plus f2 dy is equal to open surface integral of dou by dou x into f2 minus dou by dou y into f1 into dx dy. It's a very important relation with respect to closed line integral and also open surface integral. Then we are going to assume that is a constant, or simply on only two axes. Now we are going to learn about the Gauss divergence theorem. Basically this Gauss divergence theorem is going to relate the closed surface with a volume, because only a closed surface can enclose a volume. So therefore closed surface integral of f bar dot dA bar is equal to the volume integral of divergence of f bar into dV. So therefore now this is called as the closed surface with a, means closed surface can only enclose a volume. So now I have already told you f bar is nothing but f1 I cap plus f2 j cap plus f3 k cap. So dA bar is nothing but dA into n cap. So if you want to write in terms of quadrature coordinate system, which is dA bar is equal to dy dz I cap plus dx dz j cap plus dy dx k cap, and here bar is nothing but here dx I cap plus dy j cap plus dz k cap. So if you do the multiplication of these two vectors, means the dot product of these two vectors, then definitely you are going to get this one, which is f1 into dy dz plus f2 into dx dz plus f3 into dy dx. Closed surface integral of, so volume integral of, just do the divergence of this vector, which is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z into volume is nothing but the volume in a Cartesian coordinate system, which is dx into dy into dz. See, sometimes doing the surface integral is somewhat hard when compared to doing volume integral in certain questions. So then it is a very, we can easily relate surface and the volume. Sometimes doing volume, it may be seems very harder. In that case you can go for the surface integral, then you can get in an easier manner. It is up to you which method you prefer, but still you are going to get the same result no matter whatever the method you are going to prefer. It will be always going to give the same result. Some important points now we are going to study here, which is del f is a vector normal to the surface function f. I have already told you the gradient of any scalar function will be always, it is a perpendicular to the surface, and it will be always in the increasing direction of the function. And del dot f bar is equal to 0, then f bar is said to be solenoidal vector, means the divergence of that vector will be always equal to 0, means there is no divergence, means it is not going, there is nothing like outflow or inflow. So therefore simply we can say it is not diverging, means we can simply say that there is a rotational mechanism, or simply we can call it as the solenoidal vector. So the divergence of gradient of f means the divergence of gradient of f means del dot of del f. Del dot of del f. We can also call it as the del square f. So therefore, if you do this one, we are going to get here dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square. So you can write in this format. And there are two important relations which are the, see, first thing that we have learned is the gradient, then divergence, and then curl. So curl of gradient of any scalar function will be always equal to 0, and the divergence of curl of any vector function will be always equal to 0. So therefore, the curl of gradient of any scalar function will be always equal to 0, means curl of gradient of any scalar function will be always equal to 0, and the divergence of the curl of any vector function will be always equal to 0, means del dot of del cross f bar will be always equal to 0, means no matter whatever the scalar function, this property is always going to get satisfied, and similarly no matter whatever the vector function, always this property is going to get satisfied. So these things are, we are going to call it as the null identities. The curl of f bar I want to find, which is curl of f bar. See, I have already told you the important relations of a cross of b bar cross c bar. This property I have already told you. So try to make in this format, that formula, try to make it in that formula. We are going to get like this: del dot f bar into del minus del dot del into f bar. So then this is same as the previous one, but del dot del square is nothing but, this is nothing but dou square. So therefore means dou square is nothing but here dou square by dou x square plus dou square by dou y square plus dou square by dou z square into f bar. So this we are going to get in this relation. So work is basically the dot product of the force and the displacement over the lines, over the path which is going to get traveled, which is W is equal to surface line integral of f bar dot ds bar. Let me assume in a two coordinate system, which is ds bar is equal to dx I cap plus dy j cap. See, now I want to find what is the curl of f into v bar, where f is the scalar function and v bar is a vector. This is same as the, like, means uv whole derivative is equal to u derivative v plus uv derivative, like differentiation of two vectors. So in the same manner we are going to do now here. So the curl of f into v bar is equal to, see, take this f outside, so f into curl of v bar. So first we have operated on this one, now we have to go for on this one, which is del f cross of v bar. So therefore f into del cross v bar, which is gradient of f curl of v bar. So like this we have to do this one. So this is gradient of f into curl v bar plus f into curl of v bar. So like this we have to do this one. And similarly the magnitude of the del f at that point, we are going to give you the maximum value of the directional derivative of the function f at that point p. I have already told you when theta is equal to 90 degree, then only we are going to get the maximum value of the directional derivative of the function at that particular point we are going to get. So now here, this, if you do the dot product of the del f at that point, dot product of a bar by the magnitude of the vector a bar, basically we are going to call it as the directional derivative of the scalar function f at that point in the direction of the vector a bar, means we are going to find what is the component of the vector del f in the direction of the vector a bar. At that particular point we are going to figure out. Suppose if you want only the unit vector, if you are going to find only the unit vector of this gradient function, which is del f at that point by the magnitude of the vector del f, then we are going to get the unit normal vector at point p on the surface f. Suppose there is a function x of t is equal to f1 of t and y of t is equal to f2 of t and z of t is equal to f3 of t, where t is going to lie between theta 1 to theta 2, then the length of the curve will be. So then if this is the case, then what is the length of the curve, which is integration of t is equal to theta 1 to theta 2 under root over x dash of t whole square plus y dash of t whole square plus z dash of t whole square into dt. It's a very important formula. Suppose x of t is equal to f1 of t and y of t is equal to f2 of t and z of t is equal to f3 of t, and t is going to lie between theta 1 to theta 2. Then if we are going to ask the length of the curve, which is integration of t is equal to theta 1 to t is equal to theta 2 under root over x dash of t whole square plus y dash of t whole square plus z dash of t whole square into dt. So some more important points now we are going to do, which is here, see, the divergence of gradient of any scalar function, which is del dot of del f, you can also call it as del square f, which is dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square. And I have already told you we have learned about the three important concepts. First we learned about the gradient, then we learned about the divergence, and then we learned about the curl. So the curl of gradient of any scalar function will be always equal to 0, and divergence of the curl of any vector function will always equal to 0. So therefore, curl of gradient of any scalar function is del cross of del f is always equal to 0, and the divergence of curl of any vector function is del dot of del cross f bar will be always equal to 0. Suppose in the question they are asking about the curl of f bar, which is curl of f bar, but I have already told you the important formula, which is that a bar cross of b bar cross c bar. If you substitute in that formula, then we are going to get, this is the relation we are going to get, which is del dot f bar minus del square f bar. Del square is nothing but del dot del. So now what I am going to do is here, this is called as the, see, I am going to take this term to the right side, to the left side, then finally I am going to get the gradient, the gradient of the divergence of f bar, because the divergence of f bar we are going to get a scalar, so therefore this is nothing but a gradient to become. So gradient of divergence of scalar vector function is equal to curl of f bar plus del square f bar. It's a very important relation. Suppose I want to find what is the del of the gradient of L, means the divergence of the gradient of a scalar function. So therefore del dot of, this is nothing but we are going to get dou f by dou x I cap plus dou f by dou by j cap plus dou f by dou z k cap. So if you do the dot product, we are going to get dou square f by dou x cap plus dou square f by dou y square plus dou square f by dou z square. Basically it is a scalar quantity, so you can take f outside, then we are going to get dou square by dou x square plus dou square by dou y square plus dou square by dou z square into f. This is nothing but del square f. So therefore this is called as the del square, or simply we can say del dot of del is nothing but del square. Suppose if you want to do the determinant of some matrix form, then curl of gradient of f, which is curl means here we are going to basically curl del cross of del into f. So therefore simply we can say del cross of del into f. So simply we can say here this is I j k dou by dou x dou by dou y dou by dou z, and this is dou f by dou x in dou f by dou y and dou f by dou z. So you can see clearly these two rows are going to be dependent by some scalar factor f. So whenever two rows are going to be dependent, then we can say this is nothing but a dependent vectors, means one vector is going to depend upon the other vector, means we can say that determinant will be always going to give you a result of 0. And whenever the divergence of curl of any vector function will be always equal to 0, but if you want to try to figure out, this will become dou by dou x dou by dou y dou by dou z, and this is also same dou by dou x dou by dou y dou by dou z, and this is f1 f2 f3. So you can see clearly this one row and this another row, they are identical. Whenever any two rows are identical or depending by some scalar factor or by some linear function, then definitely we can say that the determinant of the matrix will be always equal to 0. So now we are going to learn about the gradients of the f dot g. So therefore if you are going to do the gradients of, means if you are going to do the gradient of these two scalar functions which are the f and g, which is nothing but f into gradient of g plus f g into gradient of f. It is same as the uv whole derivative, which is u derivative v plus uv derivative. So like this, the gradient of f into g is equal to f into gradient of g plus g into gradient of f. It's a basic formula. But if you want to the divergence of f into g, where f is a scalar function and g is a vector, then how we are going to do, which is here f into divergence of g. But if you can't directly do divergence on f, so therefore gradient of f dot product of g. And similarly curl of f into g, where f is a scalar function and g is a vector function, so therefore f into curl of g and gradient of f curl of g. So like this we have to do in order to get the result. So now divergence of f bar is equal to 0. If this is a property, we can say there is no divergence on that vector field, means it is not going outside. So there is no outflow, no inflow, or simply we can say it is a rotational vector, or simply we also call it as the solenoidal vector. So then f bar is said to be a solenoidal function. And if curl of f bar is equal to 0, means there is no curling mechanism, means or there is no rotational mechanism, or simply we can say it is a irrotational vector, or we can also call it as the conservative field. So therefore then f bar is said to be a irrotational function or field, or it is also called as the conservative field. Suppose del square f is equal to 0, means there is nothing but the divergence of a scalar function, means the divergence of gradient of any scalar function is nothing but del square f. If it is equal to 0, for this solution have neither maximum or nor minimum anywhere except at the boundaries. Means suppose if you are going to draw the graph of this function del square f is equal to 0, then definitely you are not going to get any maxima or minima between the boundaries you are going to consider. Means only at the boundaries you can get either a maxima or minima, but between them you are not going to get any maximum or minimum you are not going to get. If phi1 is equal to 0 and phi2 is equal to 0, these are the two surfaces, and given that these two surfaces are orthogonal at a point P, then it is going to satisfy this property, which is del of phi1 at that point dot product of del of f, or we can say the gradient of the scalar function at that point, the dot product, and also the gradient of the scalar function at that point should be equal to 0. Means whenever the two scalar functions are orthogonal to each other, and if you are going to try to find the gradient of that scalar function initially, the first function, and the gradient of the, say, the gradient of the scalar function at the point in that second graph also, then if you try to do the dot product of these two vectors, then definitely it will be equal to 0, because these are also going to be orthogonal to each other. Then definitely their dot product will be always going to equal to 0. And del square is nothing but I have already told, which is the dot product of the two del operators, which is del dot del, which is nothing but del square by dou square by dou x square plus dou square by dou y square plus dou square by dou z square. The component of a bar in direction of b bar, which is a bar dot b bar by magnitude of the vector b bar. So therefore, if you want to try to find what is the magnitude of the vector a bar and b bar, which is magnitude of a bar into cos theta, or simply we can say a bar dot b bar by magnitude of b bar. If you do the expansion, we are going to get magnitude of a bar into magnitude of b bar cos theta by magnitude of b bar. So you are going to get cancel off magnitude of b bar and b bar. So finally we are going to get magnitude of a bar into cos theta. So therefore simply we can say a bar dot b bar by magnitude of vector b bar. If f bar is the velocity of moving fluid, then divergence of f bar gives the rate at which fluid is originating at a point per unit volume. So basically the meaning of divergence means how much is the net amount of outflow or inflow we are going to figure out, or simply we can also call it as the, if f bar is the velocity of moving fluid, then divergence of f bar is going to give you the rate at which fluid is originating at a point per unit volume. We are going to figure out this one. Means how much amount of it is going to originate at a point per unit volume, what is the rate we are going to figure out with the help of the divergence of f bar. The curl of any vector point function gives the measure of angular velocity at any point in the vector field. Means basically the curl is going to, the curl operator is going to basically find about the, is there any curling mechanism is going to present in that field or not. We are going to figure out with the help of this operator. The amount of k into a bar is equal to, here just we can take the amount of the k bar, which is amount of k bar, because k is a scalar number, so we can take the outside, which is the amount of k into amount of the vector a bar. Suppose a bar is equal to ai cap plus bj cap, and b bar is equal to bi cap minus aj cap. So try to find the slope of this graph, slope of this vector, which is b by a, means y coordinate by x coordinate, which is b by a. So we are going to consider as slope m1, and try to find the slope of this vector also b bar, which is the y component by x component, which is minus a by b. So if you try to do the dot product of, if you try to do the multiplication of these two slopes, we are going to get minus 1. Then we can say simply that these two vectors are orthogonal to each other, or simply we can do the a into b minus b into a, or it is going to give you 0, and then in that manner also we can try to find the, it is a orthogonal vectors. So a bar and b bar are said to be perpendicular to each other because a bar dot b bar is equal to 0. A bar dot a bar is nothing but it's the magnitude of vector a bar whole square, because a bar dot a bar, if you are going to the dot product of two similar vectors, it is the magnitude of that vector whole square. And if you want to know only the magnitude of vector whole square, if you want to try to find what is the magnitude of vector a bar, then do the square root to the both sides. We are going to get under root over a bar dot a bar. So I have already told you cos theta is equal to a bar dot b bar by magnitude of vector a bar into magnitude of vector b bar. So now we are going to replace magnitude of vector a bar, which is under root over a bar dot a bar, and similarly the magnitude of b bar we are going to replace, which is under root over b bar dot b bar. And this property also I already told you, which is the magnitude of a bar plus b bar is always less than or equal to magnitude of a bar plus magnitude of b bar, because then only we can say that, as I have already told you for a triangle concept, which is the third side length should be always less than or equal to sum of the individual sides, and it should be always greater than or equal to difference of the remaining two sides. That is the meaning of this one. Work is equal to always force, it is the dot product of the force and the displacement. See, volume of a tetrahedron is nothing but 1/6 of the volume of the parallel pipe. It's a very important relation, which is the, because with the help of a tetrahedron, the amount of volume enclosed is only 1/6 of the volume of the parallel pipe. Suppose there's a vector v, which is that v1 I cap plus v2 j cap plus v3 k cap. So now I want to find what is the partial derivative with respect to t1. So therefore dou v by dou t1 is equal to dou v1 by dou t1 I cap plus dou v2 by dou t1 j cap plus dou v3 by dou t1 k cap. So any surface is represented by f of x comma y comma z is equal to 0. So generally take f is equal to f of x comma y comma z minus c is equal to 0. Suppose generally in the question we are going to use in this format as a surface. Try to take it minus c in this side and then try to now figure out this as a function f. Whenever that vector field is the gradient of some scalar function, then definitely I have told you this vector field is nothing but it's a conservative in nature. Means here the closed line integral will be always equal to 0. So therefore f is called as a scalar field and this capital F is nothing but it's now vector field. And already I told you which is divergence of gradient of any scalar function, which is del dot of del f is nothing but del square f, which is dou square f by dou s square plus dou square f by dou y square plus dou square f by dou z square. This basically we are going to call it as the Laplacian of the f. If divergence of f bar is equal to 0, then I have already told you there is no net flow or inflow, or simply we can say it is nothing but there is no, simply we can say there is no divergence field. Means basically it is a rotational field, we can say simply. So then suppose if it is a velocity of fluid, then we can simply call it as the incompressible fluid. But if it is a vector field, then we can say simply it is a rotational field, or simply we can also call as the solenoidal vector field. So suppose I want to find what is the closed line integral of f bar dot dr bar. This I have already told you, which is f bar is equal to f1 I cap plus f2 j cap plus f3 k cap. Similarly dr bar is equal to dx I cap plus dy j cap plus dz k cap. So if you do that part, we are going to get the closed line integral of f1 into dx plus f2 into dy plus f3 into dz. But if suppose if f bar is equal to gradient of some scalar function, then I have already told you the curl of that function will be always equal to 0, because curl of gradient of any scalar function will be always equal to 0. But if you try to find this curl of this function f bar, because then we are going to get this is the nature, it has to be equal to 0. It is equal to 0 only if this one is equal to this one and this one is equal to this one and this one is equal to this one. Then same thing I have written here. If this is a property, then definitely we can say that this is nothing but it is going to independent of the path. It is going to depend. This integral is going to be depend only on the initial and the final position, but it is independent of the path it is going to get travel. If dou f3 by dou y is equal to dou f2 by dou z, and dou f3 by dou x is equal to dou f1 by dou z, and dou f2 by dou x is equal to dou f1 by dou y, then we can simply say that we can simply say that this line integral is going to depend only on the initial and the final point, but it is independent of the path it is going to get travel. So therefore now here if you do the comparison, you are going to get f1 is equal to f by dou x and f2 is equal to f by dou y and f3 is equal to f by dou z. So if you do the cross partial integration and try to figure out the f, which is nothing but unit terms from k, and do the cross check, and then we can easily find this integral also we can figure out. See, the only concept of this one is if you know f1, f2, f3, try to do these things and try to see whether it is going to get satisfied or not. If this is satisfied, then blindly we can say this f bar is a gradient of some scalar function. Otherwise we can say that it is independent, or we can say it is not going to depend upon some gradient of scalar function. Then we can say it is going to depend upon the path. Otherwise it is independent of the path. So basically in these formulas we have learned some of the important points of simply we did some speed amount of revision of the vector calculus in a very much fast manner. See, if you have already learned this subject in my offline classes, then it is very much easier to do the revision of these subjects. See, I hope you have understood these lectures. So if you like the content of the channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload new video, the direct notification comes from our. If any improvements in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care and bye bye.